Okay, the first one is that we want to look at the shift in time. Okay, that was the we had already looked at this aspect. The shift in time. Okay, if you have x tilde of n producing for you in the forward transform x tilde of k, we said that x tilde of n minus m will produce for you w n k k times m x tilde of k. This is the shift in the time axis. Now, if you want to look at the shift in frequency, a similar approach, shift in frequency. Let's see if we can apply the same method that we used last time for the shift in time to apply it to the shift in frequency. So, we are going to define a sequence x1 of k, which is equal to x tilde of k minus L. So, it is a frequency shifted k minus L. Okay, so basically the Fourier series coefficient is now shifted. Now, suppose this particular sequence, this particular x1 tilde of k corresponds to time domain sequence x1 tilde of n. We want to know what is x1 tilde of n, which produces this particular relationship. So, let us write it down. X1 tilde of n will be 1 by n summation k equal to 0 through n minus 1. It will be x1 tilde of k, but I am going to just skip one step and write it down straight away at x tilde of k minus L, w n minus k n. Okay, basically we are doing the synthesis equation. So this is the expression. So just one more step and then we will get the answer 1 over n summation k equal to 0 through n minus 1. We remember when we did the shift in time, we used two properties. Okay, one was this one used the periodicity of x tilde of n, periodicity of x tilde of n. Okay. The other property that we used was periodicity of w n k m. Okay, so basically the complex exponential also has got periodicity, and we use that. So basically, if we shifted, so let's do this. Okay. So this is equal to w n k into n plus r n, any multiple of n. Okay, this will be the same. Basically, there was a periodicity here. This is equal to x tilde of n plus r n. Okay, these are the two periodicities that we utilized and we obtain. Now, we will use the similar periodicities, but now we will use the periodicity in uppercase x tilde of k. Okay, uppercase x tilde of k, and we will use the periodicity in w n k n, same as what we did last time. So I'm going to write down using this property x tilde of k minus L w subscript n. It is minus k n. I'm going to write it as minus k minus L times n. Okay, so remember that means I have introduced a w n to the power ln positive. So I must take out that contribution. So I'll multiply it by wn minus ln. Okay, so then we look at this particular term. We can take it outside the bracket, outside the summation minus ln and what we are left with is 1 over n summation k equal to 0 through n minus 1 x tilde of k minus L Wn minus k minus Ln. Okay, so basically what we have shown is that you can this is equal to x1 tilde of n. So if you take this over to the other side, okay, sorry, this is equal to the corresponding sequence that we are looking at. Let me make sure I got it correctly, plus and minus sign. Okay, and this is the x1 of n. So this is equal to Wn minus Ln. This expression, this term is the synthesis equation. So this is x tilde of n. Okay, so the result that we have is Wn minus Ln x tilde of n. This will have a discrete Fourier series given by the time or the frequency shifted version k minus L. We have used the periodicity in x tilde of k. We also use the periodicity in W subscript n and those two results. So basically we have a shift in time. We also have a corresponding shift in frequency. Okay, so we can tick off the shift in frequency as well. So this is completed. This is shift in frequency. Then comes a very important result, which says what happens when we do the convolution over one period of these two periodic sequences x1 of m and x2 of m. So, this is a different type of computation. It's a periodic convolution and it is over one period of the actual computation looks like normal convolution, but it is only over one period, and it is so the output is also a sequence which has got a period which is periodic, and it has got a period equal to n. So periodic convolution is different from linear convolution, so something that you must keep in mind. Okay, so what does periodic convolution produce? Okay, so here's the property. Okay, so let's write it down again. Because there are some very specific conditions, it is good for us to write down. Okay, so the property of periodic convolution. I'm writing it down so that you will have something to refer to, and also you will be sure that you understand the conditions under which we are looking at. Okay, so x1 tilde of n and x2 tilde of n are periodic sequences with period equal to n. Periodic sequences with period equal to n. Same period, both of them. Only then we can work with them in terms of the computation that we are looking at. And they have the corresponding discrete Fourier series representation. x1 tilde of n has got a DFS given by x1 tilde of k, x2 tilde of n has got a given by x2 tilde of k. Okay, and we are introducing, this is called periodic convolution. You can also call it circular convolution. Circular convolution. Okay, but since we are talking about periodic signals, here we will talk about it in terms of the circular convolution. Okay, the definition, also we call it as periodic convolution. So the definition of periodic convolution. Okay, we are going to define it as a third sequence x3 of n, which is summation m equal to 0 through n minus 1, x1 tilde of m, x2 tilde of n minus m. Okay, this is what is called periodic convolution. You flip the sequence and then you shift, but at all points we are looking at only a summation over n terms. Okay, so this is the sequence that we want to have. What is its DFS representation? So we also make a note that this is a signal that is periodic and its period is equal to n. Okay, so then we want to obtain the DFS coefficients of x3 tilde of n. So x3 tilde of k, let's write it down. x3 tilde of k is given as summation n equal to 0 through n minus 1, x3 tilde of n, I am going to substitute for x3 tilde of n, summation m equal to 0 through n minus 1, x1 tilde of m, x2 tilde of n minus m. So this is what is inside the bracket, and then you have the complex sinusoid Wn times Kn. Okay. So as we always do, we want to look at a shift in terms of the interchange the order of summation. So this becomes summation m is equal to 0 through n minus 1, x1 tilde of m, and then inside the second summation now is n equal to 0 through n minus 1, x2 tilde of n minus m, Wn Kn. Okay, I am going to just rewrite this as Wn Kn minus m. Because I have introduced a term, I must take it out. So that will be Wn Km. Okay, so combine these terms together and notice that this is nothing but x2 tilde of k. Okay, so we write it as x2 tilde of k, and inside the summation m equal to 0 through n minus 1, x1 tilde of m, Wn Km, and this is nothing but x1 tilde of k. Okay, so x3 tilde of k is a product of the individual discrete Fourier series coefficients. Okay, so this will be x1 tilde of k multiplied by x2 tilde of k. So it was periodic convolution in the time domain. We got a multiplication of the discrete Fourier series coefficients. x3 of n is periodic with period equal to n. Of course, x3 of n, uppercase x3 of n is also periodic with period equal to n, because product of x1 and x2, both of which are periodic. Okay, this is periodic, period equal to n. Okay, so this is the property of periodic convolution. So let us go back and tick off the property of periodic convolution. Okay, now convolution, the similar convolution, periodic convolution in frequency. Okay, I would like to leave that as an assignment for you. Okay, so this is periodic convolution in frequency. I will just write down the framework and ask you to complete it. Periodic convolution in frequency. Okay, so we have two sequences with the corresponding discrete Fourier series coefficients. Now we want to get a sequence x3 of k which has got the periodic convolution, and it's defined with a 1 over n scale factor, summation m equal to 0 through n minus 1, x1 tilde of m, x2 tilde of k minus m. Okay, so this is the definition. Now we want to find the, we don't not be x3, we can call it x2. Oh no, x1, x2 is already there. Okay, so this one will have to be x3. Okay, will that create a confusion here? X3 is defined in this way. Okay, yeah, we did not. Okay, so we want to find out that time domain sequence x3 of n, whose DFS coefficients correspond to x3 tilde of k. x3 tilde of k. Okay, and what you should do is write down the synthesis equation. X3 tilde of n is equal to, the synthesis equation is 1 over n summation k equal to 0 through n minus 1, x3 tilde of k. Instead of x3 tilde of k, I am going to write down the expression for x3 of tilde of k, which is given by this term. So we have brought in the term for x3. So what is within this red bracket is x3 tilde of k. Okay, so this is x3 tilde of k. Okay, and multiplied by the complex exponential w subscript n minus kn. Okay, and do the same thing, interchange order of summation. So step 1, interchange order of summation. Order of summation. Okay, you will obtain step 2, you will get a term containing x2 tilde of n, and then step 3, obtain x1 tilde of n. Okay, and once you have obtained these two, you will be able to verify that x3 tilde of n is equal to x1 tilde of n multiplied by x2 tilde of n. Okay, so convolution in time produces multiplication in frequency. Convolution in frequency produces multiplication in time, exactly the same as what we had for the discrete time Fourier transform. However, we are talking here about periodic convolution. That's the important thing to keep in mind, and make sure that this is not that you will not get confused by the example that we are looking at. Okay, now before we proceed any further, I want you to have an idea of what circular convolution is all about. Okay, so we have two sequences. We want to do the circular convolution. So summation, this is x3 tilde of n equal to m equal to 0 through 7, x1 tilde of m, x2 tilde of n minus m. Okay, so this is sequence number 1. This is and it is you are keeping it as is. This is sequence number 2. You will do the time reversal and shifting. Time reversal and shifting. Okay, and so let us look at it. X1 of m is the sequence that is given. The period is equal to 8. It has got 4 1s and 4 zeros. Okay. On the other hand, the sequence number 2 has got a interesting, basically it's got a variation. So let us, this is amplitude 1, 2, 3, 4, 5, 6, and this is the height of the, not the time index. Okay, so and the one is 3. So basically, it's some sort of a triangular waveform with the different slopes on the positive side and on the negative side. So it is 0, 3, 6, 5, 4, 3, 2, 1. Okay, that is the sequence that we have. Now, time reverse x2 of n. Okay, what happens? You keep 0 in its current position, everything else goes to the negative. So notice that we now have 3 here, followed by 6, 5, 4, 3, 2, 1. Okay, so basically you have time reversed it, and because it's periodic, you will find that the same sequence from this point on will repeat itself. Okay, so basically you find that the sequence is repeated. So basically, so it's a time reversal of one period, but that happens in all the periods of it. So now the new periodic sequence is the time reverse sequence. Okay, now what you have to do, you have to multiply it point by point and then obtain the value. I'm sure that is something that you are very comfortable in doing. Now I need to shift. So basically, if I want x3 tilde of 0, okay, then what I do is I will multiply these two terms and get the expression that I have. So m equal to 0 through 7, x1 tilde of m, x2 tilde of minus m. N is equal to 0. So that is the first term. So that is now if I want the second term, then I need to do these two. I need to shift one of the sequences. So x3 tilde of 1 is equal to summation m is equal to 0 through 7 x1 tilde of m, exactly the same sequence. Now it's going to be multiplied by x2 tilde of 1 minus m. Okay. Now, this is where it will become a little bit tricky to see, which way do I go? Do I shift left or right? How do I visualize it? Okay. The easiest way to visualize, as we have always said, is you have x2 tilde of n. Okay. If you want to shift it forward or backwards, then the step 1 would be x2 tilde of n plus 1, right? If you want to shift it in the forward direction, and then you do the time reversal x2. So this is a advance operation. Advance, then time reversal x2 tilde of minus n plus 1. Okay, so this particular term has got an advance operation and a time reversal. But what does it give us when you see it in the time domain? What this will produce for us is a right shift. Okay, so this is a right shift. So from here to here is a right shift by 1 unit. So look at the sequence. This now and the value number 3, which was here. 3, 6, 5, 4, 3, 2, 1, moved outside of the frame. Now this became number 3, and the first term from the next period comes in. So what you have, this is right shift by 1 unit of time. So basically you should, but what you multiply is only between 0 and 7. So what went out, ignore. What is not inside the dashed line, ignore that on both sides. Take only what is there within. And so of course, if you want x3 tilde of 2, you can see that you can get this expression here, and similarly you can try out for other examples as well. Now I want to share with you one interesting way by which people do circular convolution. Okay, so again, you can do it in many ways, but here is an interesting way by which circular convolution can be done. Okay, so this is the computation of circular or periodic convolution. Periodic convolution. Okay, so we are asked to do circular or periodic convolution of x1 tilde of n, which is a sequence that looks like this. 1, 2, 0, 1, 1, 2, 0, 1, 1, 2, 0, 1, dot, dot, dot. Okay, so this is my origin. Okay, so you recognize that the period equal to 4, and then you have the first period, the initial period will be 1, 2, 0, 1. Okay, now x2 tilde of n is a sequence, dot, dot, dot. It is 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1, 1, dot, dot, dot. Okay, so I think no need for the commas. 2, 2, 1, 1, and the origin is right here. Okay, so the focus is going to be on one period of x1 tilde of n and one period of x2 tilde of n. So a very interesting way by which people do this computation is to draw a circle. Okay, and depending on how many points are there, you take one period of x1 of n, write it on the outside of the circle. Okay, so it's 1, 2, 0, 1. Okay, so you have basically written it clockwise. Okay, so the outer one has been written clockwise. So this one is x1 tilde of n, and it has been written clockwise. Okay, now x2 of n has to be time reversed. So we will write it inside the circle, but write it in a counterclockwise fashion. 2, 2, 1, 1. Okay, so x2 tilde of n is counterclockwise. Okay, now obtain for me the product. So the first term of x3 tilde of 0 will be, let's start, 2 times 1 is 2, plus 2 times 1 is 2, 1 times 0 is 0, plus 2 times 1 is, so x0 equal to 6. Okay, now if you want x3 of 1, okay, so then what you do is this inner circle, you visualize it as if you rotated it by 1 unit. So basically the numbers are now going to change. For the first shift, this 2 came over here, this 1 went over here, this 1 went over here, and this 2 came here. So 2, 2, 1, 1, but now basically we have shifted it into a different position. Okay, so let's compute that. 2 times 1 is 2, 2 times 2 is 4, 1 times 0 is 0, 1 times 1 is 1. Okay, so this gives us a value equal to 7. Okay, I'll do one more, x3 tilde of 2. So then you write, shift it one more, so this becomes 2, 2, 1, 1. Okay, now multiply, 1 times 1 is 1, 2 times 2 is 4, 2 times 0 is 0, plus 1 times 1. So this is this is equal to 6. Okay, and the last one, like you to verify x3 tilde of 3 is equal to 5. Okay, and I would like you to verify this result. Again, this is a very easy way to visualize, and of course I will also show you how to do circular convolution using a matrix method. However, this is a very compact way, and we can get the computation. It's a good way to visualize how circular convolution is getting done. Okay, I hope you are comfortable with that, and this is basically a useful method for us to keep in mind.